All right, guys, we're going to continue waves with light. So we'll go in deeper when we get into electricity and magnetism. But for right now, we're going to talk about these things called electromagnetic waves. So we're just talking about the application of them and how they behave. Um, More details will come, but that's where we're at right now. So we're going to continue waves. The electromagnetic waves are all around us. You radio waves, Wi-Fi, Bluetooth. If you've had an X-ray recently, like that's all EM waves. We won't do all the equations. We'll see. We'll do the more straightforward ones since it is a virtual thing. C equal the one I'm going to point out right now. We'll talk about these as we go through the slides, but C equals F lambda is the one right, that's v equals f lambda from the general wave equation. C is specifically the speed of light, though. So instead of saying v equals f lambda for light, we're going to say c equals f lambda, and then c is a very specific number. It's 3 times 10 to the 8th meters per second, but we will talk about as we go. There are variations on that number, but we are going to use 3 times 10 to the 8th. All right. And so light is going to lead us. I'm going to give you. There's different light behaves differently depending on what it's doing with reflection real quick. Two-way mirrors are pretty cool. So instead of having like a solid surface where all the light reflects and you see your image, it lets like 10% of the light through. So typically you have a bright side of the room and a dark side of the room. The dark side um, is where the people hide typically, right? And they're looking through the window. What happens is the bright side lets in 10% of the light, and the people on the dark side can see it. And then it reflects 90% of the light. So on your bright side, you see your reflection. But 10% of your light's leaking through, which is sunglasses. Have you ever seen your reflection in a sunglass? Well, not your reflection. You're behind the sunglasses, and people can see their reflection. Same thing happens there. You're reflecting a good portion of the spectrum, and some of it, enough of it's coming through that you can clearly see. But we'll talk about reflection, the different applications of light and stuff like that. Measuring the speed of light, this is an interesting little side thing if you want to do it. Look up measuring the speed of light with s'mores. You can actually, well, here, I'll tell you real quick. If you melt the marshmallows or the chocolate in the microwave, not with the turntable, take the turntable out. There's videos of this if you want to do it, but take the turntable out and it'll create a standing wave like we talked about with sound waves, where you'll have a light wave bouncing back and forth, but it'll create hot spots and cold spots. That's the purpose of the tray, right? It prevents those hot spots and cold spots. But if you take the tray out, you can actually use those hot spots and cold spots to measure wavelength and get the speed of light. What is light? We didn't know. Maxwell predicted the existence of these things called electromagnetic waves in the 1860s. But what they are is alternating electric and magnetic fields, and we will talk about electric fields and magnetic fields over the next few weeks. But they can reproduce themselves they don't need a medium. They reproduce themselves. So if you got an accelerating electric field, it will produce an accelerating magnetic field. That accelerating magnetic field will produce an accelerating electric field. And that's how EM waves travel. If you just have an electric field moving at constant motion, it just makes an electric field. But if you shake it, you get a magnetic field. That's electromagnetism. We should get to that. But that's so right now we're just focusing on that light is a combination of electric and magnetic fields, and then we will talk about those fields um, as we get going. I'm sorry, I'm trying to see if I skipped anything on the slide. So when Maxwell, so by predict, he mathematically calculated these electromagnetic waves. He was looking at electric fields and magnetic fields, and then realized there was a way for them to interact with each other. And so he was able to calculate the speed of light. Now it's really 299,795,638. We're not going to use that number. Rounds to 3 times 10 to the 8th meters per second. And then like 20 years later, Hertz discovered radio waves, right? Our megahertz radio stations. We named the frequency units after him. Which hertz is an inverse second. It's right 1 over t. 1 over the period is 1 over second. 1 over a second is what we call a hertz. And then here's your v equals lambda over t. And then because frequency is 1 over t, get v equals f lambda. But we're going to be very specific about what v is. It's the speed of light. So we're going to say for this chapter, we're going to say c equals f lambda. The concept is the same though. In a uniform medium, the speed is the same. So as long as the medium doesn't change, the speed doesn't change. And so if the speed is constant, then frequency and wavelength are inverses of each other. The speed of light, like I said, is 3 times 10 to the 8th meters per second. In our units, 186,000 miles per second. So 1/1000, light's traveled 186,000 miles. It can go 7 times. It would circle the globe 7 times. In a vacuum, we approximate it as C, that 3 times 10 to the 8th. Again, it's right. It's close. It's 299. You get the idea. In glass, though, it slows down to 2/3 the speed of light. Water, 3/4 the speed of light on average. And then diamond, it drops to 1/4 the speed of light. So different mediums will interact with that light and slow it down. So then that's how you can change the speed of light. Have it interact with a new medium. What happens to the wavelength of light as it enters a new medium? Sound did the same thing, but if this is a thicker, I hate using the word thicker, denser. It has it's. I don't know that you don't want to call it density. We're going to talk about the index of refraction in a minute here, but the medium. If the medium is made up of more atoms, right? So you're going from air to water. Let's just put it that way. Right? It's a more dense. Like I'm gonna go with density. I'm gonna stick with that. But it's a more dense medium. If you're just running around and here's your wave, crest, 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 and it hits something more dense, right? Those are gonna slow down. When you run into water, you slow down. Light does the same thing. Sound does the same thing. So light, the wavelength is actually going to compact, which is what's happening in this little animation right here. I'm gonna turn on the pen first, or the laser. This little guy over here, right? The wavelength starts out pretty spread out, and then it hits this denser medium and compacts. Now, what happens at the speed? Well, to answer that, we need to know what happens to the frequencies. So then we jump to this next. So what then? That's the next question. What happens to the frequency? Well, the frequency is due to the source that's not in that medium. It's just sending out light waves, light, right? It's just sending out frequencies of light. So the frequency doesn't change. Just like sound, the frequency didn't change when you were outside the medium. Um, so the frequency is constant. So if the wavelength's decreasing, the speed of light also has to decrease when it enters a new medium. And we'll do problems measuring the speed of light. It's gonna flag me. This is the one if you want to find it. It's pretty interesting. He explains how to do it with the microwave. He actually shows you. Parts of the EM spectrum, real quick. This is price. I'm trying to think. You probably saw it in middle school, right? The EM spectrum. There's visible light. That's the part we can see, and the higher end, the higher frequency part, and the smaller wavelengths. So as the frequency goes up, the wavelengths go down, like we just talked about. You get ultraviolet, X-rays, gamma rays. On the other side, not as dangerous. You get lower frequency, bigger wavelengths. Infrared, microwave, long radio waves, or any radio wave for that matter. But that's the EM spectrum. Which is faster, gamma rays or X rays? You got these high energy gamma rays and these low energy radio waves. They go at the same speed, right? The speed of light. How does an increase in frequency affect the wavelength? I've said that a couple times. As the frequency goes up, the wavelengths goes down. So as the frequency goes up for X rays and gamma rays, they get smaller, and that's why they're more dangerous. They're more penetrating, and they can hurt us. The Doppler effect is when you shift the frequency. So here the and sound did the same thing. We had the Doppler effect with sound. This is the Doppler effect with light. The equation's the same, except instead of the speed of sound, we got the speed of light. But same rationale. The light comes out at a certain frequency from the cop car. If you're coming at it, you send it back at a higher frequency. Um, Explain how and then you can use that frequency shift to get the speed of the object. It's used if you've ever come across an automatic door. They send out radio waves, and so something stationary can just sit there and not set it off. But the second that thing moves, the radio wave that hit it comes back at a different frequency, and it knows you're trying to enter. There's also ones with infrared where it can pick up your heat pattern. So they can do it with radio waves. They can do it with not microwaves, infrared. They could do it some combination. And then this is how we actually can tell when we look out at space and they're like that it's moving away from us. This is how we know it's moving away from us. This over here, so up here is the absorption spectrum for hydrogen, and then that's at rest. So we're in a lab. We can send light through hydrogen gas, and it leaves these bands of color where the hydrogen actually absorbs some of that light, and then this is the emission spectrum that we see. Um, the and then it lines up with those missing bands. That's getting into modern physics, which we hopefully get to. That might be it's towards the end, but But if the object is moving, if the hydrogen cloud, the thing that's producing that hydrogen is moving, what we see is a shift where that red line should be. Right? It's missing that line. There should be one there, but the hydrogen is absorbing it, so we don't see it. Or at least in the absorption spectrum, we see it's missing. But it's shifted, and then as the greater the shift, the the faster it's going away from us, and we can calculate that stuff. Um, so that's all. So that's all waves in general, specific to light. Um, and then these are wave phenomena, which also are waves in general, but also we're going to talk about them specifically to light. So diffraction, I'm going to give you the definitions real quick, and then we'll go through the examples. Diffraction is when you bend around an obstacle, not through it. You're going to bend around it. Refraction, you're going to actually bend through it. Reflection, like a mirror, it's going to literally reflect off of it. And absorption, reflection and absorption are what they sound like. Absorption is going to absorb the wave. Reflection is going to release it, not release it, reflect it. Diffraction, though, is going to bend around an obstacle. And this is actually Virginia Beach. They have those stone walls to like kind of protect the beach, but there's an opening, there's a gap. And the water wave can get through. And as it's getting through, it bends and creates these wave patterns. That's how waves travel through obstacles or slit. We call them slits. As a diffraction, we call it a diffraction pattern, and that's what you're seeing there. That's the one of the big snows we had, and you can actually see the diffraction pattern on the beach. So then the question was, does light do this? So they made a slit, sent light through it, and if light was made of particles, right, the particles would just go through the slit, and you would just have one bright spot on the wall. But what we saw were was a wave pattern like this. We saw multiple bright spots. We didn't see one bright spot. We saw multiple ones. So at this point, diffraction wise, when light interacts with slits, it acts as a wave, which leads us to Young's double slit experiment. This is a video I can't show you, but if it's Veritasium, is light a wave or a particle? He goes around. He makes a box. I'm going to show you the picture he came. Don't fair. I don't know why I can never get all these videos. Might have to go back and edit this video. But diffraction and light color. So here's what you saw. Um, Now, if you did it with just green laser, you'd get a bright spot, then a dark spot, bright spot, dark spot, bright spot, dark spot. Red light, same thing, bright spot, dark spot. That's the whole diffraction pattern. And then if you do red and green at the same time, you get this like yellowish color. If you do it with white light, you get a bright white spot, and then as you go to the left and right of it, its light starts to spread out. And when light starts to spread out, you start to see its other colors. So you saw a rainbow, but you still saw bright spot, dark spot, bright spot, dark spot. That's light acting like a diffraction wave, or as a diffraction wave. And then diffraction uses real quick. It's pretty. Well, I think it's interesting. But CDs, DVDs, Blu-rays, a lot of our data readers that require light, I don't have little slits in them with holes, kind of like this. Here's B, this peacock feather, has these holes at different intervals, and we can store data that way. We can use light to read it. Spectrometer, like chemical, structural, medical analysis. We can analyze different things just based on its how light interacts with it. And then nature and iridescence. If you zoom in on the butterfly's wings here, they're these again like lines spacing, and so light comes in and bends around those spacings and interferes with itself. And then that's so this is what we did with sound waves, right? There's constructive interference and destructive interference. That's what's happening with light. So all of these have that quality. Like here's a stone, right? And then you zoom in on it, and it has these um, crevices where light has to bend around those obstacles, and it makes it look like it's like a glow to it almost. And then diffraction and DNA. This is how we how did they figure out the shape of DNA? They shined light on it. And you can do it with a spring from a pen. Take up those click pens apart, shine a laser through it up on the wall in the dark. You'll see a double helix pattern. But again, you get bright spot, dark spot. And then the variables, if uh, if we do it on a Classkick, I'll show you. I'm going to go through the variables on the Classkick instead of wasting time here. And then diffraction, bright fringe, just and it'll depend on time if we do them or not. But Conceptually, though, there will be questions like you'll be able to answer these. For diffraction, you get a bright spot, dark spot, bright spot, dark spot. If you've ever asked about the order number, like which bright spot are you looking at, you start at the bright spot, and then the next one is one. The next bright spot is two, three, four, and you can go left or right. Those are the bright spots. And then there's different numbers of slits. You can have single slit, double slit, triple slit, multiple slips, whatever. They're basically the same. You get always get a central bright spot, but then you get um, various intensities of bright spots off to the left and right. All right, so what is actually happening? Where you have a bright spot is constructive interference, like we talked about with sound. The crest lines up with the crest, so the wavelengths are always going to be multiples of each other. So they're going to be lined up as so crest and crest always, and you get a bright spot. The dark spots. So how do we number the dark spots? Well, the first dark spot that's going to be weird is 0, and then 1. But the first one is 0. And you can go left or right. And then what's happening there, same thing that happened with sound, crest with a trough, they collapse. And so their wavelengths are always going to be off by half, right? So if you have a wave with a crest and you shift it by half, now it's a crest with a trough and they collapse. Diffraction problem, again, depending on time. And then there's 2 labs this chapter. We'll pick one of them to do. I can't show you this video. This is more detail than you need, but if you're really curious, like why does light oh, sorry, this is the next thing. That was diffraction. When light hits an obstacle and bends around it, it can interfere with itself constructively and destructively, and you get bright spots and you get dark spots. Refraction is when it actually goes into the medium and bends. Why it bends has to deal with the electric fields it produces and the electric fields that it interacts with in the medium, the atom. It's interacting with the atoms. We don't need to know that detail right now. That's if we win. Ideally, we get to electricity, magnetism, EM waves, and modern like that. All that stuff will come up. But this is, if you're curious, and you want to get a jump start on that. There's a decent video from Fermilab on why does light bend when it enters glass. But and you've all seen this. If you've put a straw in a glass of water and it looks bent, right? It hits the surface and then it bends funny. You pull it out and it's fine. You put it back in. That's refraction. And then why does it bend? You don't need to know this right now, but it's the electric fields. The electric fields are interacting with the medium's electric fields. Now that's refraction is when it bends. How much it bends depends on this thing called the index of refraction, and it's based on the color yellow because yellow is right in the middle. Violet light's going to bend the most. It's the smallest wavelength, so it interacts with the medium's atoms more, the medium's electric fields more, the medium's charges, I should say. And then red light doesn't interact as much. They still all bend a little bit, but violet bends the most. So then, how do we tell how much it bends? You have to say what color you're using because it depends on the color you put through it. So this chart is based on 5.09 times 10 to the 14th hertz, which is the yellow region. We could calculate the wavelength or look up the frequency. It would be in the yellow. But air's near the vacuum of space. It's around 1. Sign it through corn oil. It's 1.47. Diamonds 2.42. You get it. Different mediums have different indexes of refraction, and that it's based on the letter N. The index just is an indicator of how much it's going to bend. All right. So how you know which way it's going to bend? This is just how I remember it, but if you go from a high, medium, high index to a low index, you go from a high to a low away. It bends away. High to low away. It's just low away, right? They sound the same. The other way to remember it is low to high toward, and it just doesn't have the same ring. But however you want to, I mean, you don't have to memorize stuff. You have access to the notes. But so here's the question: what direction will the wave bend if traveling from air low to water that's high? Well, think about yourself. If you run straight on, nothing, you're not going to notice it. You're not going to bend, right? You're going to slow down, but you're not going to bend. So you got to go at an angle. And so what happens is, if you go from air that's low to water that's high. When you hit that higher medium, low to high, you're going to bend towards it. And then that's what's happening with this. Car travels from smooth pavement, which is a low medium, to a muddy surface, which is a higher medium. Low to high is towards, and it actually, right, that picture that you're hitting that mud, and that front tire hits that mud, and the other tire that's still on the pavement pushes it towards what we call the normal line. The normal line is the perpendicular line between the two surfaces. Sorry, I left that off. Um, what medium? Oh, here in the second picture, what medium has the higher index of refraction? In the second picture, we'll see how it's bending. If it went straight through, it'd follow that red arrow, but it's bending towards medium two. Well, the only way it can bend towards if it's higher, right? Low to high is towards. If it bent away, then it would be high to low, and then they'll ask silly questions like that. The disappearing test tube. You don't need a test tube. If you have Pyrex glass at home and vegetable oil, um, you almost need two Pyrex dishes. But if you take a Pyrex measuring cup and put a smaller Pyrex measuring cup inside it, and then pour vegetable oil in, the Pyrex cup inside will as you so first do the outside with cooking oil and leave the inside air. You can see through it and you'll see the cup. But pour vegetable oil into the middle cup, and as the that volume rises of oil, the index of vegetable oil happens to have the same index of refraction as Pyrex glass. So if because they are the same, the light doesn't bend, and the light goes straight through it like nothing's there. You'll see a little bit of an image. You'll see the ink and the etchings, but it's kind of cool. Um, and then hopefully you can use the vegetable oil to cook with something. Let's don't go too crazy with the vegetable oil. So Snell's law. So how it bends can also be done mathematically, and it's called Snell's law. We'll write it this way with the n1 sine theta 1. That's the one medium, and then n2 sine theta 2. To calculate the speed in the medium, it's just the speed of light divided by the index of refraction, and then that'll tell you the new speed. But oh, here, and angles are always measured off the vertical. So these thetas here are measured off the verticals. But we'll do that in class kicks. And then this leads to a thing called Snell's window, which is the fisheye lens, which gives you this. So it takes 180 degrees and like con- condenses, not the right word, but refracts it, bends it to 97 degrees. And then more refraction examples, the rainbow. Um, are there only seven colors? No, we just simplified it down to seven colors. They believe it was Newton. There were seven. There's seven. I don't know if they're major notes, but there's seven main notes. So he thought there should be seven main colors. But if you're really looking at a rainbow, I don't know that you're going to distinguish between indigo and violet. I think that was him trying to get to seven. Mirages bend light. These are two images of mirages where this boat looks like it's floating, but that's just the light from that boat bending through the temperature difference. When you look down the road on a hot day and see that haze, like looks like haze, it's the light bending. And then the sunset, rainbows are refraction. And then the sunset's interesting. The sun, when it hits our atmosphere, the light is bending back towards us and makes the sun look like it's above the horizon still when it's actually already set. But we still see the light because it's refracting off the surface. All right, this is the lab. We'll either do the refraction lab or the diffraction lab. I think the refraction lab is more straightforward, so we'll probably do that one. And then reflection, real quick, not much to it. Angle in, we call it the angle of incidence. The incoming equals the angle of reflection, which is the outgoing. That's for flat surfaces. We will talk about what happens with curved mirrors and curved lenses and stuff like that. And then again, the angles are measured from the perpendicular. Occurs when traveling. So total, there's a thing called total internal reflection, and this is your fiber optic cables. This is why they cut gems the way they do, so that the light actually gets in to the object and gets stuck. That's total internal reflection. And it only happens, when the angle is 90 degrees for the lower index of refraction. Um, and then thin film interference is interesting. It's a combination, right? It's reflecting and refracting off this film. So CD disc, I don't know the last time we looked at a CD disc, or if you've seen like a puddle on the street and it has a sheen to it, that's thin film. Glasses, we can anti-reflective glasses. Like here you can see glare in her glasses, and then this is with a coating that's actually um, using this thing called thin film interference either to just allow certain light to go through or to be reflected or to destructively get interfered with. So you got this constructive destructive thing going on. And then that's the cause of the interference again. I'll go into this more if we do the problems. Uh, this one might be hard to do virtually. I'll debate that, but yeah, we're probably gonna skip this one. I'm gonna be honest with you, but conceptually, it's not bad. Mathematically, it takes a minute to explain, but conceptually, the same thing's happening. You have a crest with a crest, you're gonna get constructive interference, and you're gonna see glare off of glasses. But if you take that thin film on that glass and you're able to flip the wave, so now you got a crest with a trough, you can destructively interfere with that wave, and the glare goes away. So we'll see about that. And then absorption, it's what it sounds like. It absorbs the wave. If you have polarized sunglasses, they're actually the molecules in there are aligned to absorb the vertical light, and if their molecules are aligned this way horizontally, they'll absorb horizontal light. So when light hits like a flat surface, it bounces up and tends to be horizontally polarized. That's the glare you get off the hood of your car, like on real sunny days. So what they do is they put horizontal molecules, and it lets the vertical light through, but absorbs the horizontal light. And then you can tell. So when you have two polarizers and you line them up at different angles, they can block all the light, which is what's happening in this picture down here. This is polarized sunglasses, and then this is a polarized clock in a car. So if you're ever not sure if a screen's polarized, you need polarized sunglasses. But if you have polarized sunglasses, you can just cock your head a little bit, and if it goes dark, you're looking at a polarized screen. Um, Here, this video I can actually show you. I took this one. Rainbows are polarized, so you can see it through the sunglasses there. All I'm going to do is twist my sunglasses, and the rainbow disappears. Twist them back, there it is. Like you can see it coming out the bottom. But rainbows are they have a direction of light oriented with them, so when you twist the polarized sunglasses, it blocks those directions of light, and you can't see it anymore. And then here's just a cool picture. The same idea. Like people buy these polarized lenses for their cameras. You just get a cheap pair of polarized sunglasses and put it over your lens, right? Without the polarized sunglasses, you see all this glare, right? It's not the most vivid picture, but look through the sunglasses, it's perfect, right? It's perfect clear. It's absorbing all that horizontal light that's giving this bleached out look. I don't know if bleached out's the right word, but whited out. I don't know. So for photography, people use it. Sorry, I don't have it. The 3D movies make use of it. They actually send different directions of light. They used to do it. The red and blue, the old red and blue 3D glasses would absorb different. They would have. I don't exactly know. It wouldn't change the color, but the it would have two overlaid movies where, and then the red would absorb one of them and the blue would absorb other ones. Now we do with polarized light, so you got horizontal light and vertical light. But anyway, it delays the image enough that you get one image before the other one, and your brain tries to overlap them, but it overlaps them in a 3D, like it looks like it's coming at like that kind of thing. And then this is how LC. If you've ever, not all monitors, they're called liquid crystal LCD screens. But if you look at an LCD, so you have LED screens and you have LCD screens. If you have an LCD screen, you can take polarized sunglasses and turn your head, it'll go dark. LED screens, it won't do that. And that is the end, guys. Sorry, that was a longer one. All right, but we're all done. And then like I said, we'll focus mostly on concepts and hit a handful of problems like normal.